All right, so it is my great pleasure to introduce three speakers this week: Joel Scheingross, Marisa Repasch, and Niels Hovius. They'll be talking about lithospheric flexures controls on geomorphology, hydrology, and river chemistry in the Andean foreland basin. And they will be presenting it with three speakers this week. And so we're all very excited to have them. And I'll leave it to Joel. Go ahead. Sorry, Niels.
I think that I'll start. Hi, good morning, good evening, everyone. It's great to see some names that I hadn't actually expected in the live audience. I'm excited to see you. I'm the sandwich. Bread and Marisa and Joel are going to be the meat. We share a passion for a project that we have been pursuing for a number of years, for almost 8 years now, in northernmost Argentina, and I'm hoping that with this presentation will give you a little bit of an idea of why we are excited to work in this very, very flat place. We are going to talk about foreland basins. We're going to take a slightly non-conventional interdisciplinary approach to this. And yes, we are going to talk about some of the flattest places on the planet. But as a motivation, and Joel, I need the next slide. You will hear Marisa and me saying, Joel, next slide, please, because Joel is the slide meister. Before we go to flat places, I need to give you a little bit of context, and that's really my role in this whole presentation. The geomorphology community, Earth surface process community, has been working actively with many people on questions related to tectonic and climatic expressions of forcing in landscapes, and we tend to locate ourselves and look at landscapes with a high relief, and there is a natural attractor to that. One extreme example of that is this view here from the Gulf of Corinth, looking to the north at Mount Gerania, and what you see here is about 1 kilometer of limestone relief, which sits in the footwall of a single foot. Limestone in the Mediterranean climate, such as in Greece and in central Italy, is obdurate. It denudes very, very slowly. And so, in fact, what you see here is the total topographic relief of a single normal foot. At the base, the length is about 15 kilometers. I already said it's about 1 kilometer high, and you see the beautiful tapering of this fault going in both directions. So this is almost a perfect picture of tectonic forcing of topography. There's very little in terms of erosion. Joel, the next slide. In many places, there is, however, an awful lot of erosion, which is on the one hand necessary to count the tectonic influx. It's driven by climate, by precipitation, and the textbook example of this is the Southern Alps of New Zealand, where you see a knife-sharp and straight alpine fault delimiting the Australian plate and the Pacific plate, and mountains that are 3 kilometers high, only 3 kilometers high in the face of 20 to 25 kilometers of exhumation. And so you see the interface, or you see the interaction between climate and tectonics here, mediated through topography. This is our bread and butter. This is where many of us have worked for a long time. It's actually not where most people live. Joel, the next slide. Most people live in flat places. Most material that is eroded from mountain belts ends up in flat places. This is where there's an enormous amount of mass transfer, nutrient transfer, bioproductivity, and there is an enormous societal relevance to flat places. And so the question really might be, how does this tectonic forcing that is so evident in places like central Greece with extremely fast extension, or the Southern Alps of New Zealand with extremely fast uplift, how is that tectonic forcing expressed in flat places? Is it just simply buried? Does it exist? Doesn't it not exist? I mean, it does exist. We know this. So how do we get a finger behind it? And we went to flat places, actually for very different reasons. We were interested, we meaning Marisa, Joel, and I, and a number of other people there, Zaxa, importantly, in matter fluxes from mountain belts to offshore basins. But we came across a type of tectonic forcing and an expression of tectonic forcing that is really quite remarkable, and that is what we're going to show you today. Next slide, please. Now, in these flat places, rivers don't have a lot of relief, and the forcing by climate through discharge or by tectonics through slope is expressed very, very subtly. A very central concept to understand these alluvial rivers is the concept of grade, due to J. Hoover Mackin, where we understand grade, or the grade of a stream, to be that sweet spot between aggradation and degradation, where a river has just the right geometry, the channel geometry is just right to deal with the imposed hydraulic conditions and sediment load. That grade is a very precarious situation. Just a little nudge one way or the other is going to nudge or push this system, or might push this system, into a different state of behavior. And so that grade is fundamentally important in understanding alluvial rivers with such a low slope. Next slide, please. So if we want to look at the behavior of rivers with a low slope, close to grade or at grade, and we want to understand nudging, or we want to at least make use of the nudging, for example, by tectonic processes, then one setting that offers itself for study is the foreland basin system. A foreland basin is a flexural feature that exists at the margin of many tectonic loads, mountain belts, for example. To understand it, you should consider a simple beam, a metal H-beam, for example, which has a certain rigidity, flexural rigidity. It has a certain elastic thickness. And that rigidity and that thickness do set the geometry of the bending of this beam when you load that beam at a particular point. Now, the bending of the beam has a slight complexity to it. If you apply a force and the beam has a large length, and you will create a downwarp close to the load. But then beyond that, there's going to be, if the beam is fixed at the far end, there's going to be a bulge in that beam, and basically the beam will start to oscillate towards a steady elevation. And this is what we see happening in the Earth's upper lithosphere around active mountain loads. So in this image, you see a sedimentary basin which fills the subsidence, the place of subsidence that defines the foredeep close to the topographic load. And then you see a forebulge that is dominated by uplift, and a backbulge environment that is dominated by very subtle subsidence. The amplitude of these in the vertical differs starkly. So a foredeep may be hundreds of meters to many kilometers deep. A forebulge typically has a vertical relief that is just a small percentage of the total vertical relief of the foredeep, maybe 4 to 7% of that or so. And so you would expect a positive relief of maybe a few tens to a few hundreds of meters maximum. And the backbulge is really just a small fraction of that. And so it's very subtle indeed. If you change the load through changing the topography of a mountain belt or the sedimentary fill of a foredeep, then basically the rest of this flexural foreland will adjust. It will move upwards or downwards depending on where you are and what happens to the topography. So the forebulge will have a subtle uplift or subsidence signal to it, as will the backbulge, but the forebulge might be perceptible. Next slide, please. Now, people have worked on foreland basins for a long time. One of the key people working on foreland basins has been Philip Allen, who passed away last year. And he would ask simple questions of foreland basins. One of his favorite questions was how does lithospheric flexure affect the sedimentology of foreland basins? And you can flip that around and you can ask, how does the alluviated earth surface reflect the lithospheric forcing? Philip was interested in both of these things. And in this talk, we're going to offer an answer to Philip and to his questions. We're going to say, silly, it's through fluvial geomorphology, hydrology, and geochemistry. And that is exactly what Marisa and Joel will illustrate to you.
Marisa, you have to unmute.
Thanks, Joel. So we're going to go to the Andean foreland basin in South America to try to answer this question that's been posed by Philip Allen and us following after him. And so forgot to include it, but I should really give a nod to Brian Horton and Peter DeSelles, who really created this conceptual model for the foreland basin, and particularly the Andean foreland basin, where we are going to go. Next slide. All right, so we are focusing our research on the Rio Bermejo in Argentina. So that's a lowland river in the Andean foreland basin in northern Argentina. And this aerial photo just gives you an impression of what this landscape looks like. It is incredibly flat, and the Bermejo River just migrates through this, through the floodplain across the foreland basin. All right, next slide. Okay, so the Rio Bermejo is actually an excellent testbed for answering our questions about how lithospheric flexure influences Earth surface processes and sediment dynamics. So here on the left, I'm showing a map of our study area. So the Bermejo drains the central Andes and then flows for nearly 1,300 kilometers across the foreland basin without having any tributaries that are entering it. And so we can look at the fluvial geomorphology and rule out any effects that might be due to changes in river discharge or increases in sediment supply as you move downstream. And so here on the right, I'm showing some photos that show where that last tributary is at the mountain front. And then the Bermejo proceeds to flow downstream first as a braided river, and then it meanders out to the Rio Paraguay, which goes to the Rio Paraná and the Rio de la Plata. And these images also show the really high sediment load in this river system, which reflects the erosion of the Andes. And so we can imagine that any lithospheric flexure might influence the grade of the river that Niels had mentioned before. And next slide. All right, so to get an understanding of how the lithosphere is flexing in the Andean foreland basin, we looked to some modeling efforts, particularly by Chase et al., which was published in 2009. Here on the left is an image of the South American geoid anomaly, which they then used to create a model for lithospheric flexure. And here on this cross section, you can see the dipping or the subsidence of the lithosphere very proximal to the mountain front, going from about 0 kilometers downslope to about 150 kilometers. And then we see the upward flexure. So that is the forebulge from about 150 kilometers to about 500 kilometers downslope from the mountain front. And then in the back bulge, we see very, very subtle differences. And so next slide, Joel. And so the Rio Bermejo traverses this 700 kilometer transect across the foreland basin, perpendicular to all of these features. And so here we should be able to see and test whether there are effects of this differential subsidence and uplift as the river crosses the foreland basin. Next slide. All right, so we showed what the modeled lithospheric flexure looks like, but when you're in this setting in the field, there is no superficial expression. And that's because the Andean foreland basin, at least in this region, it's an overfilled basin. So it is draped by sediment. And so these photos really illustrate how flat this landscape is. But despite this lack of superficial expression, we wanted to see whether the fluvial systems actually respond to these large-scale, long wavelength lithospheric flexure features. Next slide. And so if we look back to some of the classic literature and think about the concepts of a graded river, we can look to Holbrook and Shum, who summarized what we might expect as a river crosses an axis of uplift. And here is just a schematic of a long channel profile where as the river approaches this axis of uplift, the slope reduces and the river begins to grade. Then as it crosses the axis of uplift, your slope steepens and the river system becomes more degradational. And then as we move away from that axis of uplift, we move into a zone of aggradation. And so this is the river trying to keep up with uplift. And if it can't, then we might see changes in channel slope. Next slide. And so we measured the channel slope of the Rio Bermejo. And here on the top, I'm showing a plot of that slope. And what we see is a really stark decrease in channel slope moving from the mountain front downstream. And then we see this transition to more increasing slope and variable slope moving downstream. And this slope break lines up with this transition from the foredeep to the forebulge in the model by Chase and others. And so we interpret this as the river adjusting its grade to the subsidence and uplift across the foreland basin. And these photos to the right show examples of what the river looks like in these regions. So the top picture is an example of where the riverbed is aggrading, and that is in this upstream reach between 0 and 110 kilometers downstream. And then in the forebulge, we see evidence of riverbed degradation. All right, next slide. So in addition to changes in channel slope, a river might also respond by changing its width and its sinuosity. Again, in this conceptual figure from Holbrook and Shum in 1999, they gave some examples of what we might expect for a river crossing the axis of uplift in terms of its channel planform. And so upstream of this axis of uplift, we see a wide channel belt. You might have a braided river. And then as you cross that axis of uplift, the river is forced to narrow its channel and actually becomes highly sinuous as a result of that uplift. Next slide. And so we measured the channel width of the Rio Bermejo, and we also measured the width of its channel belt. So everywhere where the river is actively migrating. And so what we find is that the channel is wide and braided in this upslope portion of the river near the mountain front, and up to 10 kilometers wide in some places where the river is very braided. And then we see this stark decrease in channel width and channel belt width at about 150 to 200 kilometers downslope. And then the river becomes this narrow single thread channel that is highly sinuous. And that continues moving downstream. And so these places where this channel width breaks also apparently seemingly line up with these foreland basin features. Next slide. And something that's interesting, in addition to the increase in sinuosity moving from the braided reach into the meandering reach, we also see really high lateral channel migration rates. in this reach above the forebulge. So here on the top, I'm showing lateral migration rate with distance downslope. And in the braided reach, we don't really consider this a lateral migration rate. These are the rates of the river channel moving within the channel belt. But then we move into the region of forebulge uplift, and then we actually measured rates of up to 30 to 50 meters per year of lateral migration. And this video on the right shows how rapid that migration is. So this is a sentinel images from 2015 to 2019, showing this meander bend cutoff, and then it continues to grow rapidly shortly after that. So that indicates that the channel is highly unstable in this reach. And then as you move out of the forebulge, we seemingly see this turning off of lateral migration rates, where the rates are incredibly low. And so these features remarkably also line up with the modeled locations of these lithospheric flexure features. Next slide. All right, so the next thing we might want to test is whether the channel is aggrading or degrading, or whether it's super elevated above the floodplain or incised into the landscape. And what we might expect as a river crosses the axis of uplift is that just upstream of this region of uplift, we might expect the river to experience overbank flooding. So as it's aggrading during flood seasons, the water might spill out of the channel. And then as we cross the axis of uplift, the river should then switch to incising into that uplifting landscape to try to maintain grade. Next slide. And so we actually observe this region of overbank flooding just upstream of where we expect to see forebulge uplift. And so we're not actually the first people to observe some of these geomorphic changes in the Rio Bermejo as it crosses the foreland basin. This image from Maglu and others was published in 2016, and they pointed out where we see changes in the channel width and sinuosity. But this Landsat image also shows regions where the soil moisture content is quite high, suggesting that this region is prone to overbank flooding. And so this region also lines up with this transition from the foredeep to the forebulge. Next slide. And in addition to the overbank flooding, we also find that the channel is super elevated above the floodplain in the foredeep, and then incised in the forebulge. And so this top figure here is the elevation of the floodplain above the river channel. So any place where this black line is below zero is where the river channel might be sitting above the floodplain. And then with the floodplain elevation above the channel, that is everywhere where the river is incised into the floodplain. And so we see these trends moving downslope from the mountain front, from the river being super elevated above the floodplain to overall incised up to 5 to 10 meters into the floodplain. And then as we move out of the forebulge, the river seems to remain incised, moving downstream. And that's likely because we don't have any real changes in subsidence or uplift in that area. And this photo on the bottom right of this slide shows an example of where the river is incised in the area of the forebulge uplift. Next slide. And so to explain how we derive that floodplain elevation above the channel, just briefly, we essentially subtracted the elevation of the floodplain from the elevation of the channel long profile to create this map of the landscape using a DEM. And you can see that these features are persistent across the foreland basin, not just within the river channel. And Joel will talk more about this and how we see patterns of geomorphic patterns of this uplift and incision across the basin. Next slide. All right, so that was a lot of geomorphic and morphometric analyses. And so I just want to summarize it. So we showed that channel slope, width, incision, channel migration, and sinuosity all seem to have changes moving from the region of modeled foredeep subsidence to forebulge uplift. And so this suggests that these fluvial adjustments suggest that the flexural uplift, even though it seems so subtle when we're in the field and looking at this landscape, that this uplift can profoundly influence the landscape and the ability of rivers to move sediment and water from upstream to downstream across these basins. All right, next slide.
Okay, great. So Marisa has really painted a picture of how these flexural, how this lithospheric flexure is really affecting the morphology. In this next section of the talk, we want to ask the question of whether or not this is affecting hydrologic flow paths and how that might affect the geochemistry of the system. So to do that, I'm going to remind you of this point that Marisa just made, that we see these really stark changes moving from the foredeep to the forebulge. That in the foredeep, where we have subsidence, we get this braided channel that's super elevated. And in the forebulge, where we have uplift, we get this channel that's really, in size. 5 meters of incision may not sound a lot to you, if you're working in steep landscapes. But in this really flat landscape, when you come up to this section of the river, it's quite shocking and was a bit unexpected to us at first. And again, I'll point out that we've quantified this with this relative elevation map that Marisa was just showing. So on the top, anytime you're plotting above this line of 0, it means the channel is incised. Below 0, the channel is super elevated. And we see in this zone of foredeep subsidence, we have a lot of super elevation of the channel. This really only happens in the foredeep. And in the forebulge, we get a channel that is almost always incised into the floodplain. And in the back bowl, this amount of incision decreases till we reach the Rio Paraguay. So we can use this to come up with a couple hypotheses about how these flexural changes might actually control the hydrology. So if we move to the foredeep, we're going to hypothesize that the super elevation makes the Rio Bermejo a losing stream, or that water in the Rio Bermejo, discharge in the Rio Bermejo, is being lost to the groundwater. And this is because the river is sitting higher than everything else in the landscape. So the groundwater table should be sloping away, and we're going to lose water. If there's overbank flooding, that water is going to go into the groundwater table. It's going to be hard for it to come back. And this is in contrast to what we expect in the forebulge. There, the river is deeply incised. It becomes one of the lowest places in the landscape. And this should create a gaining stream, or there should be a net groundwater influx into the Rio Bermejo within the forebulge. And because groundwater is often enriched in solutes, we might expect an increase in the dissolved load within the forebulge due to this groundwater influx. And so the best way to test these hypotheses would be if we could go out and have groundwater wells that were of scientific monitoring quality everywhere in the region and actually measure the slope of the groundwater table and look for the groundwater table sloping away from the Bermejo in the foredeep and sloping towards the Bermejo in the forebulge. Unfortunately, this is a really rural part of Argentina, and that type of infrastructure simply doesn't exist. So we can't test this hypothesis that way, but we can test this hypothesis using a few other clues that I'm going to walk you through. So the first is we're going to look at downstream changes in discharge along the Rio Bermejo. If we have a losing stream, we should get a decrease in discharge moving downstream. And the second thing we're going to do is we can actually look at the geochemistry of river water. So we'll collect and analyze water samples, and we'll look for evidence of this groundwater influx, which we expect should have an increase in the solute flux in the river. And we could also look to see if there's any evaporation, because if we see downstream losses in discharge, some of that could be due to surface water moving to the groundwater, but some of that also could be due to evaporation. So I'm going to start first by looking at downstream changes in river discharge. And again, we're a bit data limited here, that it would be nice if moving all along the Rio Bermejo, we had nice gauges everywhere, and we could, quantify what's the discharge coming in and out of the foredeep, coming in and out of the forebulge, and coming in and out of the back bulge. Unfortunately, we don't have that. These are the 3 gauges that we have. And so what we're going to do is we're going to combine these 2 upstream gauges to get a sense of what the net water flux is into the foredeep. And we're going to compare that with this gauge down here, which basically tells us what the water flux is coming out of the forebulge. And if we look at 40 years of data, what I'm plotting here is daily mean water discharge on the Y versus day of the year on the X. The dark blue line is this combination of the 2 upstream gauges. The light blue line is the downstream gauge. And what you can see is that for the most of the year, especially during the wet season, the upstream discharge is much higher than the downstream discharge. So this is weird, right? Like typically discharge increases downstream. That's what we expect from basic hydraulic geometry principles. But here, depending on how you calculate it, averaged over the entire year, we get a net loss of about 20% discharge moving from upstream to downstream. So it seems like water is being lost somewhere. Again, I'll point out this is a really rural region of Argentina. There's not a lot of water being drawn from the river for human use. We did quantify that where it exists, and it's a couple percent. It can't really explain this 17 to 24% loss in discharge. So either somewhere between the foredeep and the back bulge, we have a losing stream, or there must be a ton of evaporation happening in order for us to get this big loss in discharge. So I want to test that idea, and we're going to test that by looking at samples of water from the Bermejo to look at evaporation and also see if there's solute flux coming in, which we would expect to happen with groundwater. So we sampled water all along the Rio Bermejo and in some of its headwater tributaries over 5 different sampling campaigns, 3 in the wet season, 1 in the transitional season between the wet and dry, and 1 in the dry season. And in a few places, we were also able to access groundwater wells. I'm showing those as these stars here to get a sense of what the groundwater geochemistry is. So I want to take these samples we've collected, and I first want to ask the question, is this discharge loss that we're seeing here, could that be due to evaporation? And the way we're going to test that is by looking at water isotopes. If you're not familiar with water isotopes, I'm going to give you a quick primer on it. So what I'm plotting on the right, these are delta 18O, so oxygen stable isotopes on the X, delta D, deuterium on the Y, and all the data that you see in this space is precipitation, some that we collected in the field, others from existing databases that are close to our field area. And what you can see is precipitation in this isotope space plots along a straight line that we would call the local meteoric water line. And what we can do is, if there's evaporation, we expect evaporation is preferentially going to take up the lighter isotopes, which means material or water that's left that's not evaporated is going to get heavier. So in this space, that's going to plot like this. Oxygen is more sensitive to this than deuterium. So we basically get a decrease in the slope of this local meteoric water line. So when I add data from Rio Bermejo water to this plot, if water we collect in the river is plotting along this line, it looks the same as precipitation, we're assuming that there's really no evaporation. And if it's plotting out here, then there is evaporation. So let's look at some of that data. I've now taken the precipitation off for clarity, but I'm still plotting this local meteoric water line. The axes haven't changed. And the circles are all water samples we've collected from the main stem Rio Bermejo and some of the headwater tributaries. And they're color coded according to if we collected it in the wet season, transitional season, or dry season. And the gray stars are the ones from these groundwater wells. And what you can see is the vast majority of the data here is plotting along or near the local meteoric water line. So this really suggests that there's minimal evaporation along the length of the Rio Bermejo. And we also see that the groundwater is plotting along the local meteoric water line. So groundwater input isn't causing any change in these water isotopes. Yes, there are a few places in the Bermejo where we do see evaporation. This is really in select locations, and we see it during the transitional and dry seasons where we might expect there to be more evaporation. But I'll also point out there's periods in the transitional and the dry season where we have water samples plotting along the local meteoric water line. And most of the discharge loss that we see moving upstream to downstream happens in the wet season. So it really doesn't seem like evaporation can explain this net downstream loss of discharge. So thinking back to this hypothesis that the foredeep is a losing stream, well, we do see that there is this discharge loss moving from the foredeep to the back bulge. And I would make the argument to you that the most likely place for us to have this discharge loss would be in the super elevated foredeep. That's a zone where we would expect to be losing discharge. But this discharge data alone can't really nail that question. So if we really want to know, is the foredeep a losing stream? Then we also have to answer our second hypothesis or prove our second hypothesis. And if we're systematically gaining discharge, or we have some groundwater input that we can document in the forebulge, then it would seem most likely that this discharge loss is happening in the foredeep. So let's look at the second part, the second hypothesis, that in the forebulge, because of incision, we're actually expecting to gain some discharge and have this input of groundwater. And again, we're going to test that using the river water geochemistry. So what I'm plotting now is total dissolved solids on the x-axis, and this is basically distance downstream from the Bermejo along a straight line on the x. Sorry, it's total dissolved solids on the y. And I've shaded the forebulge here in gray for you to see. The colored symbols are all samples from the main stem Rio Bermejo, but I first want to draw your attention to the black stars. These are the groundwater wells that we were able to sample. And I'll point out that the y-axis here is on a log scale. And I hope the first thing that really jumps out at you is that the groundwater has 5 to 10 times higher solute concentrations than the rest of the river water. So if there is groundwater input into the Rio Bermejo, we would expect to be seeing that with an increase in solute load moving downstream. And so you can see that a bit here in these November 2019 samples. These have higher total dissolved solids than all the other samples. This is during the dry season. And we do see this increase here. And in fact, there is an increase in TDS across all of these samples too. These are our 4 other sampling campaigns. It's a bit hard to see in this plot, so I want to plot the data a slightly different way. So now I've kept the x-axis the same in the plot on the right, but I'm now taking a normalization of the solute concentration. So I'm taking total dissolved solids at this location here in the year we measured it, or I'm using this location to normalize. So I take the value of total dissolved solids and I normalize it by this location. So they all come to 1 here. And now we can see the fractional change moving from upstream to downstream. And what I hope you can see here is in the back bulge, we don't see that large of a change in total dissolved solids. Samples are staying relatively constant, but we do see this really distinct approximately 30% increase in solute concentration moving across the forebulge. And then in the back bulge, solute concentration stays fairly constant. So this seems to support really both of our hypotheses, that this increase in the solute load in the forebulge is consistent with the forebulge being a gaining stream. We know groundwater in this region has really high solute concentrations. We see an increase in solute concentration in the main stem channel. There's not really a lot of evaporation happening there, so we can't explain the increase in solute concentrations from evaporation. So the forebulge being a gaining stream seems the most likely explanation of this pattern. And if that's true, then we also need to assume that the foredeep is a losing stream because we need to lose discharge somewhere. And because we have this net loss of discharge moving from the upstream end of the foredeep to the downstream end of the forebulge, this gaining stream in the forebulge still can't make up for all the water that's lost in the foredeep. So I'll also point out, I haven't talked that much about the back bulge in this section of the talk. Here in the back bulge, we're getting a relatively constant solute load with distance downstream. So this suggests there's either a lack of groundwater influx in this region or that the sediment is perhaps chemically depleted. I want to investigate that a little bit more, and I'll go back to this residual elevation map that we've looked at before, and just remind you that in this top plot, things plotting above this 0 line need incision. So the back bulge starts in size coming out of the forebulge, but incision is really decreasing because we've lost this lithospheric flexure. There's basically no flexure in the back bulge, maybe a tiny bit of subsidence. And one of the responses to that we can see in this residual elevation map on the bottom are all these brown squiggly lines of relative incision. And these are actually springs that are incised into the floodplain. So we're on kind of the toe of the Rio Bermejo megafan. This is what some of these streams look like. Here, Niels is for scale, much smaller than the Bermejo. And we've gone and we've measured the solute load and the conductivity in many of these springs. And not all of them, but many of them will have high solute loads, suggesting that they're draining groundwater. So in this region in the back bulge, we have the emergence of these springs and ponds, and that suggests that we may be transitioning to a more parallel flow regime, where we still might have some groundwater influx, but a lot of the groundwater is being sent to these other streams that are emerging, or springs that are emerging. And so we're not seeing these large changes in the geochemistry in the main stem Rio Bermejo within the back bulge. So to wrap up this part of the talk, we've seen some really cool connections between how the tectonic setting is affecting the geomorphology and how that's then affecting the hydrology, where in the foredeep, we have this losing stream because the river is super elevated. And then in the forebulge, the river incises. Some of that groundwater can come back in. That increases the solute concentrations. And then in the back bulge, we move to this parallel flow regime where we have more limited interactions between the groundwater and surface water. And this whole idea that we're putting forward here has some implications for thinking about chemical weathering in foreland basins. So I'll first make the point that super elevation in the foredeep is allowing sediment to be stored above the water table, but in areas that are prone to seasonal inundation. So this may promote weathering. But if you think the foredeep is this zone of really intense chemical weathering, and one wants to measure that, one of the most common things that is done in geochemistry is to say, okay, this area is weathering a lot. Why don't I just grab a water sample at the downstream edge of the foredeep and the upstream end of the foredeep? And if I compare the geochemistry between those two samples, I can measure the amount of weathering happening along this transect because we assume that rivers nicely integrate what's happening above them. And this is an example of where that approach would break down, that there's this really rich interplay between surface and groundwater dynamics that affects the ability of fluvial dissolved loads to really accurately capture local weathering. So if you want to measure the amount of weathering that's happening in the foredeep from a sample of river water, you'd actually have to take that sample down here at the end of the forebulge where all of this groundwater is coming back in, and then you're going to get some combined signature of weathering in the foredeep and the forebulge. So again, there's this really rich interactions here that really stems from the tectonic setting affecting the geomorphology, which then drives the hydrology, then affecting the geochemistry. So with that idea, I'm going to turn it back over to Niels to zoom out a little bit.
Yeah, and I'll do that in just a few minutes to allow for time for discussion. Just a very quick summary of what Marisa and Joel have told you. Essentially, what they've painted is a picture of a segmented foreland with a foredeep that at the moment contains a superelevated river system that is losing groundwater into lower parts of that foredeep away from the channel, but that, as a result of very little input of water and input of solutes, is in fact chemostatic. Downstream of that sits a forebulge section where the topography is gently nudged up, where at this moment in time the river is incised into the uplifted paleotopography containing other incarnations of this river, suggesting that there is avulsion at times and a relocation of the whole system, and where hydrologically groundwater is contributing to the discharge of the stream, and that groundwater is charged with solutes, and so as a result the chemistry of the river changes, and it changes quite dramatically. And then in the far field, far away from the mountain front, we see this back bulge area that is characterized by topography with a much finer scale to it, and groundwater flow that may be semi-parallel to the surface water flow. That groundwater flow may be in part fed by a little bit of exfiltration from the channel, but much more likely it is fed by a range perpendicular drainage of groundwater on much longer length scales, maybe even from the foredeep all the way across the forebulge and into this back bulge area, feeding these smaller channels that crop out parallel to the main channel. So that is the picture that we have, Joel. I want to end by very briefly looking at three different aspects of this. First of all, in the introduction, and Marisa as well, we spoke about flexure and about the somewhat fuzzy geophysical constraints on flexure. I've explained very briefly that two fundamentally important controls on the nature of flexure are the flexural rigidity and the elastic thickness. Flexural rigidity and the elastic thickness of the lithosphere. When I was a PhD student, there was a hot debate about these, and really there was a cottage industry in inverting geophysical data, especially gravity data, for information about those crustal properties. Here, we can use the geomorphology, the hydrology, and the geochemistry to define where the forebulge is, to get a pretty precise handle on the width of the forebulge, which is half a wavelength of flexure, and we can plug that number together with some reasonable and pretty robust assumptions about the density of the crust, the density of the lithospheric material below the crust, the gravitational acceleration, Young's elastic modulus, and Poisson's ratio, and plugging all these numbers in, we get numerical constraints on the geophysical parameters of this or characteristics of this particular setting. So we can actually put a pretty precise number onto both the rigidity and the elastic thickness. Those numbers are not alien numbers. They do agree, or they sit within a range of values that are assigned based on geophysical considerations to these foreland settings. Here we demonstrate that we can use these surface observations to come to pretty crisp estimates, local estimates of this. Joel, next slide. Joel has already argued that there's weathering happening in these forelands. There's a lot of sediment. The sediment is fine-grained. There's very little coarse-grained sediment, in fact, in these systems. So there's enormous surface area, and the sediment residence time is rather significant in some parts of these foreland basins. If you combine that with a lot of groundwater through flow, then it's easy to imagine that there's a lot of chemical activity in the subsurface of these foreland basins. I want to zoom out a little bit and look at the importance of this of weathering in a more general way. There's been a long-standing debate about the relationship between erosion fluxes and weathering fluxes, where for a long time it was assumed that when you erode fast, you refresh the weatherable surface area, mineral surface area at a high rate, and therefore you're going to get a high weathering rate, and therefore a high carbon dioxide drawdown rate. Now, carbon dioxide gets only drawn down by weathering through the weathering of silicate minerals with carbonic acid. There's, however, a completely different weathering system which involves not carbonic acid but sulfuric acid, and not silicates but carbonates. And if I combine a sulfuric acid with a carbonate, then basically I release carbon dioxide. Now, it just so happens that in rapidly eroding areas, the fast geochemical processes which involve the oxidation of pyrite, the formation of sulfuric acid, and the dissolution of carbonate rocks, even if they're minority constituents, completely overwhelm the much slower chemistry of the silicate weathering with carbonic acids. And so we understand more and more that mountain belts are places of release of carbon dioxide through inorganic weathering reactions. And instead, you need time and an emphasis on the slower reactions that are involved in silicate weathering in order to draw down carbon dioxide. In a paper that hopefully will come out very soon, Aaron Buffy with collaborators is demonstrating this, and is actually finding that there is a carbon dioxide drawdown optimum at very limited weathering, very limited erosion rates of maybe 0.05 to 0.1 millimeter per year. And those are in fact the rates that one might expect in forebulges, for example. And this puts a real emphasis on the role of these forebulges in a global biogeochemical sense. They may be hotspots for carbon dioxide drawdown due to the very specific combination of geophysical nudging and hydrological organization into in a geomorphological setting. Now, final slide, Joel. There's one other dimension that is important here, and I should really emphasize that what we're looking at here is a snapshot of a river system, a very dynamic river system with some of the highest channel migration rates on the planet, especially in the meandering part in the center of this picture. At the moment, we have this tripartite organization of the system, but only 150 years ago, the river was in a completely different location, farther to the south, in a place that still contains a few % of the total discharge of this area. And what is easy to see is that in the foredeep, where now there is super elevation of the channel, there might at some point be an avulsion of the channel into a completely different lower bit of the topography that would draw all discharge out of the current incised channel. It would basically cause ponding of water and sediment in the foredeep, and at some point that might overtop the gently uplifted forebulge topography, but in a different part, in a different segment of that forebulge. And so you would actually bring a lot of water and a lot of sediment onto that elevated topography. And rather than finding an incised channel straight away, you would find a wetland. If you go one river farther to the north, the Rio Bermejo, which is only 100 kilometers away, and I don't have the same residual topography map for that, then you would find on the forebulge not an incised channel, but in fact a picture that is shown below the residual topography map, and it shows a river that basically is all over the place and a giant wetland as a result of that. Eventually, this may entrench and you go back to a Rio Bermejo type setting, but there is an enormous cyclicity to this whole system, which is really important also for understanding the immediate geomorphological expression of this system, the hydrology, and the geochemistry of the system. So it's not a static picture, it's a highly, highly dynamic picture. Joel, next slide. So then the conclusion of this presentation is its title, Lithospheric Flexure Controls, Geomorphology, Hydrology and River Chemistry in the Andean Foreland Basin. And we believe this is not only the case in the Andean Foreland Basin, but in many filled or overfilled foreland basins. I have been bowled over by the expressions of geophysical processes in this utterly flat landscape. And this image of an incised meander bend is really one of the most striking pictures that I have ever seen of geophysically uplift controlled fluvial response. We have come to this river not to do this type of work and to look at these interactions, but rather we were attracted by the fact that here we have a stream that is 700 kilometers long as the crow flies, 1,300 kilometers long if you measure along the channel, and it doesn't have any significant tributary or distributary. It's probably the largest flume on Earth. We use it to look at the processes of load transfer long distance across continents through fluvial processes, the transformation of these loads. And these loads we understand to be clastic sediment, but also the organic load of this stream. And we've worked hard to quantify these fluxes, their transformations, and their timescales, and come up with a series of hard quantifications and some very surprising insights. And so there's a whole bunch of papers that I would encourage you, if you're interested in this topic in general and in this location in specific, that sits behind this presentation, which are not listed here, but they're easy to find, and I hope that you will enjoy some of the work. Now, all that is left for me is to thank you for listening. We're looking forward to questions, and most of all, I want to thank the many people who've contributed to the work in the Rio Bermejo over a number of years. At the GFZ Potsdam, where both Joel and Marisa were when they started to work on the Rio Bermejo. Dirk Sachse, Kristen Cook, Sophia Dosch, and Hella Wittmann have been very important in contributing their expertise and their workforce to the work here. Manfred Strecker has organized a substantial amount of funding for work in Argentina in general, from which we have benefited, and Marisa's PhD was funded through that. Oscar Orfeo, who has facilitated enormously within Argentina, and a lot of the logistics, but also a lot of the local understanding we wouldn't have had without his input. Riccardo Zupiani, Francisco Lato in Santa Fe have played similar roles, and our very faithful driver, Yanni Rojo, who is pictured here in the center or in the left top, has always accompanied and has always kept us safe. Thank you for listening, for watching, and we look forward to your questions.
All right, thank you to all of our speakers. Thank you, Niels, Marisa, and Joel. The chat is open for questions. If you have a question and you would like to type it down, please feel free to do that. I see that we already have a couple. We'll read them out loud in a minute. If you'd rather ask your question in person, use the reaction button at the bottom of your screen and raise your hand, and we will ask you to unmute and you can ask your question in person. But I will start with the first question by Danny White. Is the high sediment supply from the mountains the primary driver of the high slope channel superelevation in the 100 kilometers of foredeep, rather than an aggradational response to meet grade as a response to the lithospheric uplift? Whichever one of you wants to answer it, go ahead.
I guess I can speak to that. So yes, I think you wouldn't be surprised that many rivers draining high relief mountain fronts will enter the foreland basin and have that extreme reduction in slope and aggrade their stream and become super elevated. But it's really the transition from the super elevation to the incision that is so stark that we don't see in other foreland, well, in other river settings. That really drives us to the hypothesis that it is the lithospheric flexure. Does anyone else have comments on that?
Yeah, one small addition to that is that in many other forelands, proximal forelands, there is a strong grain size reduction and something called the gravel front, and basically that is one important driver of the change of slope in that part of a foreland basin system. In this particular case, there's actually the whole system that we've shown you today is formed of very fine sediment. There are very minor grain size trends only along this section, and so we're not looking at slope changes that are primarily grain size controlled.
Great. Or do we want to add anything
I was
else?
going to say, I think that's good if you were waiting for me.
Okay. Thank you, Joel. So we have another question from Hannah Davis. It says, very interesting talk, thanks. Do you see a difference in the vegetation type or density between the foredeep, forebulge and backbulge regions?
Marisa, this is something you've worked on.
Yeah, so we did look at vegetation types across the foreland basin to see if they do change in response to changes in groundwater level with respect to the floodplain surface. But it's also a little bit complicated by changes in precipitation gradient across the foreland basin. And so I think it's hard to say, but certainly when we move from the forebulge out to the backbulge, with the change in groundwater table, we see introduction of more tropical wetland plants that really saturated soils. And I think that's the strongest effect that we see. Whereas in the forebulge, it's really subtropical forest that is with pretty dry soils.
Yeah, and this is also related. There's another question later on about aridity, which is also controlling some of the vegetation changes that actually moving from the mountain front all the way out to the Rio Bermejo, we see a net increase in precipitation that you get wetter as you're moving out into the back bulge. And that's controlling some of these changes in vegetation. And an increase in precipitation should also mean that we would have more water entering the channel and that we wouldn't have this losing stream, but we don't seem to see that.
One interesting aspect of the ecology is that in the transition between the forebulge and the backbulge area, there's a very striking and strong gradient in the ecology, which cuts across a much softer gradient in the precipitation. And so it really appears that some of the ecology is again controlled by flexure.
Okay, so the next question is from Fred Phillips, and I see that he is online. So would you like to ask the question yourself, or should we do that?
Sure, I'll ask it myself. So my question, first of all, great talk, really enjoyed it. The observations indicate that you have about 5 meters of incision in the forebulge over presumably a fairly short period of time. So if you extrapolate that over millions of years, you should get a substantial topographic feature, positive feature, and you don't see that. And so the most logical way to get that is that you have sedimentation in the foredeep that is keeping pace with the uplift of the forebulge and maintaining that grade. And so if that is indeed the case, then you could test the accuracy of the geophysical calculations by getting some measure of the sedimentation rate in the foredeep, presumably, as you approach the forebulge, so that you don't have to worry about complications from tectonic subsidence in the main part of the foredeep. And that should then equal approximately, at least, the calculated rate of uplift of the forebulge. And I was just wondering whether you attempted to do that kind of calculation.
Shall I answer briefly to that? Thank you, Fred. What you have to keep in mind is that there's an enormous lateral mobility to this river system. As I said towards the end, 150 years ago there was a major revulsion, and so the 5 meters of incision that we see now is a feature of the last 150 years. Whether that incision is going at a pace that is suggested by that time scale and that depth over geological time, I would doubt. Frequently, this river switches into a new position and does the same thing as it does in this position. And so you can't just say, okay, now we accumulate all of this vertically. No, it's accumulated laterally. So rather, if you want to have another test of our geophysical numbers, so to speak, then you can go into the foreland, the foredeep basin, and look at its stratigraphy. I would argue that that's a very expensive approach. That is in this particular setting not at all feasible, and so you're actually compelled to use these very cheap and cheerful approaches that I think we've shown today to get some constraint on at least on the properties. The rates, that is a completely different question, and that's something that we haven't actually addressed. It would be much more expensive in terms of time and in terms of analytical capabilities to address that, and I doubt that you will get a full picture, because the same processes that actually build the aggradational record also destroy the aggradational record, and so you don't get a complete image.
Thank you.
All right, in that case, we'll move on. We have a couple more questions. We'll try to go over them quickly, as I want to be mindful of time. I think Joel answered David's question, so I'll go to the next one by Ahmed Yacoub, which thanks you for the informative presentation. And he asks about the average amplitude of forebulge uplift, and if this uplift could cause river diversion instead of increase of incision of the river crossing the forebulge.
Niels, do you want to talk about the Tocomayo here?
Yeah, not this. I've already mentioned the Pilcomayo, which has a very similar local relief and forebulge relief as the Rio Bermejo. It looks virtually identical, and yet it's in a completely different phase of the cycle. At the start of the talk, I very briefly said that the magnitude of forebulge uplift is very minor, just a few % of the subsidence in the foredeep. So if you have a kilometer of foredeep subsidence, then you will only have a few tens of meters of forebulge uplift. We're not talking about a great deal, but you spotted that a river may be very sensitive to this, and just a little bit too much uplift or uplift too fast may actually cause a complete deflection. Now, there are other forelands that are not as filled or overfilled as this foreland, that instead contain marine areas, or so seas or lakes, and those are narrow zones, wet zones, that are trending parallel to the strike of the orogenic structure, and they're bounded on the outboard by minor topography, hills a few tens to a few hundred meters high. At one site, you can't address where tipping point is, but that would be an interesting question. What do you need to do to this particular system to tip it into a state where the river can't actually cut across the forebulge anymore, but is deflected by the forebulge? If you go farther to the south in Argentina, you actually do come across that particular configuration where the forebulge has a topography of many tens to a few hundreds of meters, jagged hills, and the little bit of drainage that comes out of these more arid places upstream of that particular part of the forebulge is not capable of carving a path through, and instead is ponded in big saline lakes and just escapes only occasionally.
Brilliant. Thank you. So I'll move on to the next question from Suzanne Anderson. She says, wonderful talk. Joel, I was surprised not to see an estimation of solute flux from the forebulge region. Also, any indications of weathering reactions involved silicate versus the pyrite oxidation carbonate weathering Niels discussed?
Yeah, thanks, Suzanne. So the solute flux, it's a little tricky because you really want to do a full concentration discharge analysis. So we can do that in the places that we have gauges, but it's hard to do that in other places because we know that the discharge is changing. Yeah, it becomes, a little bit circular to use the precipitation or to use the gauge data and the solute data to do this inference of where that's happening. So we can do that in a few places, but again, it requires lots of samples over a long time period, and we have really few samples from the dry season to do this type of concentration discharge analysis. So I do have some estimates that I can share with you later if you're interested, but it didn't feel robust enough to go into this talk or into this paper. And then in terms of what are the actual chemical reactions involved, it's something we should dig into, but it's not something that we've done that analysis yet. So yeah, stay tuned. Maybe to add just a little bit on this, there's virtually no carbonate in this in this foreland. There's also precious little pyrite. The chemistry is dominated by silicate weathering, but there may also be an important biological control, and so where most of the elements go up in concentration as you go down the river, actually silicon goes down dramatically, indicating that algal activity may be important, and that might also set some of the other chemical patterns.
Okay, this seems to be the end for our questions, and I think it's a good time for us to conclude. We will not be back again next week. This is the end of our fall seminar. We'll be back for our spring-summer seminar, which we will decide on in a later date. When it will start, we'll decide on a later date. Thank you again for the speakers. Thank you for the excellent talk. It was really, really enjoyable. And thank you for agreeing to have this really cool three-person, three-headed speaker version. Thank you, everybody, for joining us. It's been a pleasure.